Hi, chemistry students. We're here with a quick video to discuss a little bit more about binary ionic compounds, particularly those with what we call multivalent metals. So multivalent metals are metals that can have different charges. They are not in group 1 or group 2, where they're +1 charge always or +2 charge always. They can change their charge depending on what they're bonding with and the conditions around them. And because of that, they can form a lot of different types of compounds, and it can be a little bit confusing. So you might have noticed with binary ionic compounds, writing formulas can be really easy, and there's a pattern that you should notice. The first pattern that you should notice is that if the cation and anion have equal and opposite charges, the formula has no subscripts. So Na with a +1, Cl -1, NaCl. Ca +2 and O -2, those are equal and opposite, so you get CaO, you need one of each to make a neutral compound. Then we have Al +3 and P -3 will make AlP. There's no subscripts because the +3 and the -3 cancel. The second thing you might notice is that if the charges don't match, the numbers are often swapped. So let me show you an example. And you drop the signs. So here we've got Na +1 and O -2. And it's kind of like the 1 goes down there and the 2 goes down there, and we drop the signs. And Na2O would be the way you'd write that formula. Another couple of examples here. Al +3 and O -2, you'll have Al2O3. So the numbers kind of crisscross. Ca +2 and Cl -1, you get CaCl2. So those are some patterns maybe you've noticed, and they usually work. There's a little bit of tricky stuff you might see occasionally. Let me go back one here. So for example, if you had Ca +2 and C -4, then it wouldn't be Ca4C2, it would be Ca2C, because 2 calciums would give you that 4 positive charge to cancel out the 4 negative on the carbon. But for the most part, it works. So those multivalent metals, not all transition metals are multivalent, but many of them are. And some metals that are outside of the transition metal group also can be multivalent as well. So for us, we're just going to assume that if it's a transition metal, it's multivalent. If it's not a transition metal, it's not, unless otherwise specified. So that's not technically correct. Technically, we should make you memorize all the multivalent metals. And if you took AP chemistry, you probably would have to do that. So let's see, because they can have various charges, we have to specify their charges in the names of the compounds. So here are a couple of examples. Manganese with a +3 charge can bond with fluorine with a -1 charge, and it makes MnF3, and we call that manganese 3 fluoride. That's how we say it, manganese 3 fluoride, but when we write it, it's in parentheses, Roman numeral 3, III. Manganese with a +5 charge can also bond with fluorine, and it makes MnF5, and we call that manganese 5 fluoride, Roman numeral V for 5. And Mn +3 and O -2 will make Mn2O3, and you have to call it manganese 3 oxide. Again, we know manganese is a transition metal. Let's just review here what those are. Transition metals are these sections here, and of course these guys down here also are often multivalent, so we'll use Roman numerals with them. So anything in that middle block of the periodic table, you're going to use Roman numerals in the name. Notice the formula has numbers in it maybe, but never Roman numerals in the formula. So again, here's your common charges. And so the elements we're talking about are the pink ones in the middle that don't have the purple bands through them. These are the transition metals that are going to be multivalent usually. I'm going to pause for just a second. Okay, so here's some examples of writing formulas. And so with multivalent metals, you have to pay attention to the charge, and you need to make sure charges are balanced, of course. And we're going to use the table like we did before, where you've got the name, the cation, the anion, and the formula. So iron 2 chloride, we're going to write the formula for that. So we're going to say, okay, what's the iron 2 ion look like? Well, we don't have to look up iron's charge because we know that Roman numeral tells us the charge. It could be different charges, but we know which one that's going to be here. So that's Fe plus 2 is the iron 2 ion. If it said iron Roman numeral 3 chloride, we'd have Fe plus 3 here. Now we do have to look up chlorine. Chlorine's a halogen, so it's a -1 charge. And then we're going to make the formula from that. And if you think of it in terms of the crisscross method, you'll have FeCl2. Now we're going to do iron 2 oxide. Again, the iron 2 ion is Fe with a +2 charge. Oxide is O with a -2 charge because we look it up. It's in the -2 column. And so when we put those two together, iron 2 oxide has no subscripts. FeO is the answer. This is a little tricky because a lot of times kids will see the Roman numeral 2 and think there has to be a 2 in the formula, like there was in FeCl2. But in FeO, there's no 2 there. And the reason, again, is because we need one of each, Fe plus 2 and O minus 2, to cancel each other out. On this one, we're going backwards. We're trying to write the name. So this is going to be nickel phosphide of some sort. But nickel is a transition metal, and it's multivalent, so we have to figure out its charge. So first thing we're going to do is look up phosphide's charge, because that's set in stone. It's always -3, because it's in that -3 column. So then we ask ourselves, okay, which nickel is going to bond with a P-3 to make NiP, no subscripts? Well, it's got to be whatever cancels this P-3 out, so it's got to be +3. So then we can figure out our name is nickel 3 phosphide. So it's a little tricky. You're kind of working backwards on this one. Here's another example of the same sort. Tungsten, W, could have lots of different charges, and we don't know which one it's going to be. But we do know that it's bonding with phosphorus here, and phosphorus is -3. So think about which tungsten, that's going to be a W here. What charge on tungsten would we have here so that 3 of those would cancel out 2 phosphoruses? Well, 2 phosphoruses at -3 each gives you -6 charge. So what charge must we have to get +6 if we have 3 of them? And if you think in terms of the crisscross method, we're crisscrossing backwards. So we're taking that 3 that's on the W here, and it becomes the charge on the P. So what must the charge be on the W? Well, it must be 2. So this is going to be called tungsten 2 phosphide. Okay, I hope that helps explain a couple of little details with the multivalent metals and some extra practice with balancing charges in ionic compound formulas. And you have one more little check for understanding to do, and let me know if you have any questions.